Hi, I'm Harrison Leary, and this is my Physics 2211 Lab 5. So, the goal of this experiment is going to be to predict and analyze the motion of a slinky being dropped using physics principles. So, the video that we're going to look at is of a slinky that is stretched all the way and is relaxed, and then the top of the slinky that it is hanging from is going to be dropped, and we're going to analyze the result of that change in force. So we will measure the data from the video and then compare it with a coded model. So the physics principles that will be used are the gravitational force, which is mg times the negative j hat direction. We also use Newton's second law. We will use the spring force, which is the negative spring constant times L minus L naught in the L hat direction. And then finally, we will use the velocity and position update formulas. So for the experiment, this is the video that was provided and used for the data collection. The initial slinky length was calibrated to an estimated 1.5 meters, and the initial position was selected at 0 meters and the initial velocity at 0 meters per second. So for the analysis of the motion, there are only a few frames to work with as it's very fast, but that is the motion that was collected. And with that data, as you can see on the right, it is staying relatively still. And then once the top of the slinky comes down, that is when it starts to move the slinky. So what I consider to be happening is that when the slinky is here and it's let go, the center of mass of the slinky is moving, but the bottom of the slinky is not moving. So once the center of the mass and the bottom of the slinky become the same point, that's when the bottom of the slinky will actually register that the slinky is moving, and it will fall to the ground as seen here. So then for my model, here's all my code. So we have the estimated ball, or the estimated slinky mass, which was found in a study from Stanford, was where I collected that. We've got the initial position and velocity as discussed earlier, and regular G is 9.8, J hat, so on, so on. Then I took the times based on the collected data in the video. So for the first 0.4667 seconds, the gravitational force is equal to the spring force, and all of that is listed here using the velocity formula, the position update formula. F net is equal to gravitational force plus spring force. They cancel out, they equal each other, and so on. And then once 0.4667 seconds have passed, that is the next 0.2 seconds is where the center of mass and the bottom of the slinky are at the same point. Therefore, there is no spring force and only the gravitational force is being applied on the slinky. And then we can see the result of that in this video. So here we have the, originally it's the force is not, or the position is not changing because the position to the bottom of the slinky does not change while the center of mass is falling. And then at this point, at 0.4667 seconds, the center of the mass and the bottom of the slinky overlap, and that is when the force of gravity starts to take effect and the slinky accelerates down at 9.8 meters per second squared. So then the results I have here, they do vary quite a bit, but there are quite a few errors that may have had an effect on this. So first of all, the big one, the video was very fast, and since YouTube compresses footage, there were also very few frames to work with within that 0.667 second time frame. So there were some discrepancies in that little bit of time where the slinky was actually falling, only about 7-ish frames to work with. So shows that jagged change in position on the measured model. However, the overall shape of the graphs remains similar, so I do consider that the model is an accurate, semi-accurate representation of what is going on in the Slinky video. And that is all. Thank you.